We're used to seeing the solar system as a neat cosmic racetrack, planets orbiting in perfect loops on a flat, organized path. But what if we shift our perspective? What if we flip the system on its side and explore what lies above and below that familiar orbital plane? In this video, we will take a vertical journey through the layers of the cosmos, from the icy frontiers of the Kuiper Belt to the heliosphere's invisible shield, and all the way to the mysterious Galactic Halo, to reveal the unseen dimensions that truly define our solar system's place in the universe. The Kuiper Belt, traditionally considered the boundary of our solar system, spans from about 33 to 55 astronomical units from the Sun. But recent discoveries are challenging that notion. The Subaru telescope in Hawaii, working with NASA's New Horizons mission, has identified 11 icy objects between 70 and 90 astronomical units. This hints at the existence of a second Kuiper Belt, separated by a puzzling 15 astronomical unit-wide gap between 55 and 70 astronomical units, where no objects have been observed. This second belt could represent a new structural feature of the solar system, one that reshapes how we view the outer regions of our stellar neighborhood. The Subaru telescope's Hyper-Suprime Cam enabled this breakthrough by imaging deep into the sky with extraordinary clarity, now that Pluto and the Kuiper Belt have moved out of the dense stellar backdrop of the Milky Way. These distant objects are likely just the beginning. Their detection suggests a much larger population of icy bodies in this zone, a region once thought to be empty. The discovery also challenges previous assumptions that our solar system is unusually compact. Similar multi-belt systems have been observed around other stars by telescopes, like ALMA in Chile. These belts are believed to play crucial roles in shaping planetary orbits, and in the delivery of volatiles, such as water, to rocky worlds. The implications stretch even further. The student dust counter on New Horizons continues to detect high levels of dust impacts far beyond the known Kuiper Belt. Coupled with unexplained stellar occultations, this suggests the presence of more undiscovered bodies. The structure of this potential second belt may also help explain the peculiar orbits of objects like Sedna, or offer new clues in the ongoing search for the hypothetical Planet 9. If confirmed, Kuiper Belt 2 could revise our understanding of how planetesimals formed and migrated during the solar system's infancy. Dr. Fumi Yoshida, a key researcher in the discovery, notes that a larger solar nebula could mean planet formation was more extensive and chaotic than previously thought. Beyond the outer edge of the Kuiper Belt lies the heliosphere, a colossal bubble inflated by the solar wind that envelops our entire planetary system. This region marks the boundary between our Sun's domain and interstellar space, acting as a cosmic force field against galactic radiation. At its boundary lies the Helopause, where the solar wind slows dramatically and interacts with the interstellar medium. For decades, scientists speculated that a hydrogen wall might exist at this frontier, a zone where interstellar hydrogen piles up due to the collision between solar and galactic forces. NASA's New Horizons, equipped with the ALICE ultraviolet spectrograph, has been instrumental in probing this region. By measuring Lyman alpha emissions, a signature of excited hydrogen atoms, the spacecraft detected elevated ultraviolet signals consistent with the presence of accumulated hydrogen. However, a recent study published in the Astronomical Journal provided new insight. After isolating solar contributions and filtering background noise, researchers found that the emissions likely come not from a dense wall, but from broader structures. Hot interstellar gas bubbles created by supernovae millions of years ago. These findings suggest that the Helopause is not a rigid boundary, but a fuzzy transition zone shaped by turbulence, magnetic fields, and relics of stellar explosions. The Sun and nearby stars may be moving through one of these hot bubbles, remnants of past cosmic violence. Understanding this region is vital for mission planning. Cosmic rays and interstellar particles can damage electronics and pose risks to future crewed missions. Mapping the boundary's structure helps engineers design better shielding and navigation protocols for deep space travel. Additionally, the observations from New Horizons contribute to broader galactic cartography. The Lyman Alpha map produced by the spacecraft offers the first complete picture of how ultraviolet light behaves across the entire sky from beyond 50 astronomical units, helping astronomers understand the local galactic environment in new ways. Extending far beyond the sun's sphere of influence, the galactic halo emerges as a vast and elusive component of our galaxy, an enormous, spherical structure of stars, gas, and dark matter that envelops the Milky Way. Unlike the visible spiral arms of our galaxy, the halo is a ghostly region, detectable only through its gravitational effects and sparse ancient stars. Recent observations from Gaia and the Canada-France-Hawaii telescope revealed stars up to 1 million light-years away that remain gravitationally bound to the Milky Way. This discovery nearly doubles previous estimates of the galaxy's size and points to a more massive and extended halo dominated by dark matter. Dark matter in the halo helps keep galaxies intact and governs the movement of stars in their spiral arms, but it may also influence the solar system in subtle ways. Tidal forces from the galactic center, or passing dark matter clumps, could disturb the Oort cloud, a distant shell of icy bodies located thousands of astronomical units away, sending long-period comets toward the inner planets. The galactic halo also stores remnants of smaller galaxies absorbed by the Milky Way over billions of years. These mergers may have disrupted early solar formation or contributed raw materials, like metals and dust, necessary for building planets. Our solar system is thought to currently reside within a low-density region known as the local bubble, carved out by supernovae around 10 million years ago. As the sun drifts through this bubble and eventually into denser regions of the interstellar medium, it could experience varying radiation levels and dust interactions. Missions like Interstellar Probe and ongoing data from Voyager and New Horizons will be key to studying these transitions. Such missions offer not only practical data for spacecraft durability, but also cosmic insight into how planetary systems evolve under the influence of their galactic context. Thank you for watching. Subscribe for more incredible journeys across the stars. Until next time, keep looking up.